An experimental diving bell is lowered from rest at the ocean surface and reaches a maximum depth of 80 meters. Initially, it accelerates downward at a rate of 0.1 meters per second squared until it reaches a speed of 2 meters per second, which then remains constant. During the descent, the pressure inside the bell remains constant at 1 atmosphere. The top of the bell has a cross-sectional area of 9 meters squared, and the density of seawater is 1,025 kilograms per meter cubed. For part A, you want to calculate the total time it takes the bell to reach the maximum depth of 80 meters. So this part of the problem has nothing to do with fluids, this is just pure kinematics. And it's a slightly more advanced kinematics question, so pause the video right now, give yourself a few minutes to try and get the answer. You should get a total answer of 50 seconds. If you get that, then skip on to part B. But if you don't get that, here's the solution to it. We have to break this problem into an acceleration part, where it's speeding up, and then the constant speed part. So for the acceleration part, you know that it starts from rest, so the initial velocity is 0. The acceleration is given as 0.1. The final velocity is given as 2, and you want to find the time. So just use the real simple equation, v equals VO plus AT. Since the initial velocity is 0, we can cross that out and solve for time, which is V over A. So 2 over 0.1 equals 20 seconds. So it accelerated for 20 seconds, and then it starts moving at a constant speed. Now you know the only equation you can use for constant speed is V equals delta x over t. So since we want to solve for time again, t is equal to delta x over v. And we know the speed is 2 meters per second, but we don't know how far it has to travel, because the total distance was 80 meters, but while it was accelerating, it traveled some of that distance. So we're not just plugging in the 80 meters for the delta x. So we've got to go back to the acceleration part of the problem and solve for that distance. So I'm going to call it the delta y, which is question mark. So you can use any of the equation now, except for that one that we just used, because it doesn't have a delta y in it. So I'm going to use the one v squared equals VO squared plus 2a delta y. The VO, again, is equal to 0. So rearrange for delta y, it is v squared over 2a. So 2 squared divided by 2 times 0.1 gives you a distance of 20 meters. So since the total distance was 80 meters and we went down by 20 meters in this part, that means there are 60 meters left to go. So the time for the constant speed part is 60 divided by the speed of 2, and that gives you a time of 30 seconds, which means your total time was the 20 seconds plus the 30 seconds, or 50 seconds. For part B, calculate the weight of the water on top of the bell when it is at the maximum depth. So if you think about the shape of the water on top of the bell, it's just going to form a cylinder going from here all the way to the top. So it's this long cylinder from the surface of the bell all the way up to the surface of the water. So we can calculate the weight using Fg is equal to mg. Mass is density times volume, so we have rho Vg, and the volume is going to equal, for the cylinder, is the surface area of that circle, so it's that area which was given as 9.0 meters squared, times the height of the cylinder, which is the depth, 80 meters. So we can write this as rho times the area times the height in place of the volume times g. So this is going to be 1,025 times the area, 9, times the height, 80, times the 9.8, and you get an answer for that of 7.2 times 10 to the 6 newtons. For part C, calculate the absolute pressure on top of the bell at the maximum depth. The equation for the absolute pressure is the surface pressure, which in this case is at the surface of the sea, which is atmospheric pressure, plus rho GH. Atmospheric pressure, you can just plug in 1 times 10 to the 5th, plus the density of seawater, 1025, times G, times the height, 80, and that gives you an absolute pressure of 9.0 times 10 to the 5th pascals. For part D, on the top of the bell, there is a circular hatch of radius 0.25 meters. Calculate the minimum force necessary to lift open the hatch at that maximum depth. Well, this is where you have to take into account the fact that there is a pressure of 1 atmosphere that is actually inside the bell. So in here is the pressure of 1 atmosphere, and that pressure will basically balance out with the pressure at the surface. So we don't even need to worry about this PO right here, because the pressure at the surface balances out with the pressure inside the bell. So as far as the pressure inside, as far as the pressure required to open it, it would only be this part of the equation, essentially the gauge pressure. But then you have to get the force, which is pressure times area. So F is equal to P times A. The pressure is the rho GH times the area. This time it just gives you the radius, so you have to figure out the area of the circle using pi r squared. So now you can plug in all of these numbers. 1025 times 9.8 times 80 times pi times the radius 0.25 squared, and you get an answer of 1.6 times 10 to the 5 newtons. And for part E, what could you do to reduce the force necessary to open the hatch at this depth? So if you just think about it in terms of this equation, there are 2 things you can do. You can reduce the pressure, and this is the overall pressure, or you can reduce the area. So reducing the size of the hatch is the obvious answer to say, since F is equal to PA. But how do you reduce the pressure of all the water that's on top of it? And to do that, instead of reducing the pressure of all the water on the top, since you have to stay at the same depth, you could increase the pressure inside the bell. So increasing the pressure inside the bell would not only compensate for that surface pressure, the PO, but it would also have taken into account some additional water pressure that would be canceled out with it as well. So the 2 most obvious answers are reduce the size of the hatch or increase the pressure inside the bell.